So our example problem that we have here is taken from the 2008 Mechanics for Response questions, where we have a skier that is traveling downhill. It is a frictionless hill, so we don't need to be concerned about friction, but we do have an air resistance force here. And that air resistance force can be modeled by the expression F equals negative BV. We are also told in the problem that all of our expressions and our answers may be in terms of capital M, that's the mass, that constant B, our angle theta, and any fundamental constants. So things like G, the gravitational acceleration, will allow to be in our expression. The first thing we need to do, just as we do with any force problem we approach, is to draw a free body diagram. So pause the video right now, draw your free body diagram, and come back to it to check your solution. Your free body diagram should include the gravitational force pointing straight down, the normal force perpendicular to the surface, and that drag force. I'm just labeling that with an F since that's the variable given to me. The length of these vectors does not matter in this case, just that they have the correct direction and correct labels. Part B is one of our new things, and that is to write a differential equation that can be used to solve for the velocity of the skier. As we learned previously, that differential equation should have both the velocity and the derivative of velocity in the same equation. So we're going to start out with the net force equation like we typically do. And when we have ramps, we often do the net force parallel to the incline and the net force perpendicular to the incline. So parallel to the incline, I have the component of the gravitational force parallel to the incline and that air resistance force. And those that add together equal mass times acceleration. And perpendicular to the incline, I have the normal force and the component of gravity perpendicular, and that equals mass times the acceleration perpendicular to the incline. Now we know that the skier is not going to be accelerating perpendicular to the incline because his skis will remain in contact, hopefully, with that hill the whole time. So this expression becomes 0. And really, if I'm trying to find velocity, normal force has nothing to do with velocity, and gravitational force has nothing to do with velocity. So in reality, this whole expression is not useful here. And if this were actually on the AP test, I wouldn't even bother writing it because it doesn't get me to my end goal. So instead, we'll focus on the forces parallel to the incline. So I know that I can find the gravitational force parallel to the incline by doing the magnitude of that gravitational force times the sine of theta. And I'm going to consider downhill to be the positive direction. My air resistance is opposite the positive direction, so I will subtract that magnitude B times V. And I know that my skier is going to accelerate down the incline, so M times A. Now, I'm going to express FG as M times G here because M and G are both variables I'm allowed to use in my final expression. And instead of A for acceleration, I'm going to make use of the fact that I know acceleration is the derivative of velocity with respect to time. So I'll plug that into my expression here. And I now have a differential equation that has both velocity and the derivative of velocity. So that's all I'm looking for in part B is that expression. Part C then is asking us to find an expression for the terminal velocity, or as we've learned, this is the time where the acceleration is equal to 0 because the net force is equal to 0. So looking at that expression that I have up here, I would have mg sine theta minus bv, and this is the terminal velocity in this case, for I'll put a t on there, equals 0, since acceleration is 0. All I have to do here is do some algebra to solve for this terminal velocity, and I would find that it's equal to mg sine theta divided by b. Watch the next part of this video in order to learn exactly how to solve this differential equation.